All right, here we are, solving linear equations. So we've been working our way towards it. We're finally here. I'm very excited right now. This is the biggest thing maybe that we're gonna learn this semester. I don't know. We learned lots of good stuff, but this is a good one of my favorites. Okay, so our whole motivation, big part of our motivation here, was to be able to solve systems of linear equations. So so I have some ax equals b, right? Okay, so how are we saw some special cases if if a is diagonal, some cases where we can sort of do it easily. But what about just in general? Can we come up with some solution here? And the answer is yes. And the way we're going to do it, there's more than one way, but the way we're going to do it is to use QR factorization. So remember from before, we said that any invertible matrix A can be turned into the product QR, where Q is an orthogonal matrix, orthonormal columns, and R is an upper right diagonal matrix, right? So that means this thing here, we can say, okay, ax equals b, and then we're going to replace that with QR x equals b. Now, because Q is orthogonal, we can replace that, or we can multiply both sides by Q transpose, right? So we get Q transpose Q R x is equal to Q transpose B, right? And then those cancel out. So I end up with Rx is equal to Q transpose B. And Q transpose, that's a very easy thing to figure out, right? So that just leaves this R on the left-hand side here, and we've got to try and figure out somehow how we're going to how to get that on the other side. In essence, to do something like R inverse R x is equal to R inverse Q transpose B, right? But we're not going to explicitly calculate the inverse, although it is invertible. R inverse Q transpose B, like this. Now we've solved the x. We've managed to solve for x here. But what we're going to do instead of explicitly calculating the inverse, we'll come back to that in a second. Let's think for a second about diagonal matrices and what that means from this point of view of solving a system of linear equations. So let's make up a diagonal matrix. I'm going to try and pick one that doesn't have too many weird numbers in it. So there's going to be a lot of ones in my thing here, but let's do, I don't know, a 4 by 4. 1, 2, 0, negative 1, negative 1, 4, 1, I don't know what, 2, 3, negative 2. Okay. And then this part here is going to be zeros, okay? So this is our R right here, and then we need some B also, because we're doing Rx equals B, right? So we'll make up some B that's just going to be a 4 by 1 vector, 1, 0, 3, 8. Wait, I don't want big numbers, I want small numbers. 2. Okay? Okay. So if we were to express this, if we were to sort of like rewrite it in like the traditional algebra form, we would be saying something like x1 plus 2x2 minus x4 equals 1. And then negative x2 plus 4x3 plus x4 is equal to 0. And then 2x3 plus 3x4 is equal to 3, getting v3 here, right? And then lastly, we have negative 2x4 is equal to 2. Okay, so just like rewriting this the system, going from matrix notation to just sort of the old-fashioned linear algebra notation here. And then, so if we look at the way the system is set up here, we can start at the bottom, and x4 only depends on itself. So that's an easy one. I can solve for x4 already, right? Divide both sides by negative 2, and I get x4 is equal to 2 over negative 2 is equal to negative 1, right? And then I can plug that in. Into this equation over here. So now I have 2x3 plus 3 times x4, which is negative 1, equals 3, right? So this is, 3 times negative 1 is negative 3. I can add 3 to both sides, and I get 2x3 equals 6. X3 is 3, right? And then going up to this one, I can do the same thing. I can do the same thing here, and now sort of plug in both, right? So I get negative x2 plus 4 times x3, which was 3, plus x4, which was negative 1, is equal to 0. 12 minus 1 is 11, so I get negative x2 is equal to negative 11. It's very possible I will mess up the arithmetic here. Really, the point is, hopefully you can kind of see how this is going to pan out, right? And then last one, now we have values for x2, x3, and x4. We didn't actually need x3, it turns out, but that's fine. So now we can say x1 plus 2 times x2, which was 11. This actually worked out really well. I'm surprised. I'm surprised I never got any funky fractions, but that's good. Minus x4, which we said was negative 1. Like I said, it's very possible I will mess up the arithmetic here. This is when it's nice to be in front of a live class, because then someone will point it out to me when I mess up. Is equal to 1. Okay, so then this is 22 plus 1 is 23. We subtract 23 from both sides, and we get x1 is equal to negative 22, I think. Right? Whether the details of that specific piece I don't think matter a ton. The point here is the algorithm, right? So the algorithm is start from the bottom, and solve for x4, and then use that to solve for x3, use that to solve for x2, and use that to solve for x1, and sort of work your way filling in the diagonal here. And that will work for any right triangle where the diagonal is non-zero. If the diagonal has zeros in it, then it's not invertible. It's nothing you can do. Well, I mean, there's some things you can do, but we'll get to that later. And this exact same argument would work for a lower triangular matrix also. I'm not going to go through it, but if you had a matrix where the upper part were zeros and the lower part were was the upper part is zeros and the lower part is numbers, then you could do the exact same thing. Just start from the first element, solve. And this is a kind of back substitution. I think maybe let me make sure that's what they call it in the book. Yeah. Okay. So this whole thing, this whole process of solving for an R matrix, maybe I'll make it bold. So if I have something like this of the form Rx equals B, right? Then I solve that with back substitution, so-called because we are just substituting back in, running out of space, substitution, right? Okay, so that's great because that means going back to our sort of overall picture here. Let's come back over here now. Our strategy here is going to be to compute the QR factorization. So find the let me shrink it back a little bit here. Yeah, that's about right. So we're going to say find the QR factorization, and then multiply Q transpose times B, and then solve Rx equals Q transpose B using back substitution, right? And so this is our general algorithm here for solving a system of linear equations. We finally got there. We used a lot of the pieces along the way, but we can finally do it. We know how to find the QR factorization of a matrix. Multiplying the transpose is easy, and then we have this final piece of solving a triangular system with back substitution. So let's think about like how expensive this whole process is. So the QR factorization, we talked about this before. That's a big O of n cubed operation. If you haven't heard of big O, that's fine. But actually, I think that it's 2n cubed. It's about 2n cubed operations to find this QR factorization here. Multiplying Q transpose by B, well, how much is matrix vector transpose going to cost? N squared. What about this back substitution that we were doing here? This is an interesting one because it's this diagonal thing, right? I just did an example here, but let's try and sort of like formalize our back substitution algorithm, right? Let's try and sort of formalize our back substitution algorithm. Actually, I'll just do it wherever I wrote it before. Where did I write it before? Here we go. Beautiful. So, what's that? Okay. So our algorithm here is we're going to say for I equals n down to 1. So starting at n and working our way back to 1, right? We're going to say that x sub I is equal to b sub I minus the sum of R. Okay, so let's think for a second. Let's look at our example and kind of think through what this is supposed to look like. So we want for each of the starting, so I is going to start at n and it's going to work its way this way. This is the diagonal, right? And then for each one, we're going to start with b sub I. That's here. So think like in this example, we say b sub I minus all of the other pieces here, right? So that'll be let's make some new index j that starts at I plus 1 and goes up to n, and we're going to say rij, that's that thing, times x sub j, right? The one that we've already found, divided by r I, right? So starting at n, so x sub n is going to be equal to b sub n over rnn, and because it's the biggest one, that sum term doesn't do anything. Then the next step, it's going to be, and maybe I'll even write this out just because to make it like seem sort of more clear here. So you know, unrolling this loop a little bit, so it's going to be like x sub n is equal to b sub n over r n n, and then x sub n minus 1 is going to be equal to b sub n minus r n minus 1 n. That's like, in our example here, that would be the 3, right? This 3 here. Times x4, x sub n, divided by r n minus 1, n minus 1, right? And then the next one, we would subtract off the next 2, and then the next 3, and so on. Okay, so this is our algorithm for back substitution. Okay, so how expensive is this? Well, just as like a rough, like back of the envelope thing, we've got a for loop here that's going over 1 to n, and then we've got this inside, we have this sum, which is also in some sense like a loop, going from j equals I plus 1 to n, right? So like in your head, you can think kind of ballpark, it's probably going to be something n squared. And in fact, as we sort of, let me actually go back to our example with 4 here really quick. So for the x4 one, I had to do one floating point operation here, right? And then for the next one, I had to do this multiply, and then a subtract off, and then this divide at the end, right? So that's 3. Okay. And then the next one would be 5. And then the next one would be 7. Each time doing those, you know, the multiplications and these others. And so the overall thing here, anytime you have this sort of sum thing, we talked about that before, its overall sort of like size is going to be n times n plus 1 over 2. So this sort of like overall thing is n squared. It's, rather than trying to do it, I may just look at what it says in the book, because I don't want to spend too much time on this part of it. But let me just, yeah, so it's n squared. Yeah, so this whole thing here it ends up being exactly n squared, as it turns out. Okay. Sorry for the diversion here. So this thing is n cubed, this thing is n squared, this thing is also n squared, right? Which means that the biggest step by far is still finding the QR factorization. And this whole process, it's still going to be approximately 2n cubed floating point operations to do. And those n squareds, they're sort of less important as the size of the thing goes on. Okay, so this was, you know, so this is our big thing. We can solve any system of linear equations using about n cubed flops for an n by n matrix. One other thing that I wanted to point out about that is because the back solve is relatively cheap. Let's say you have several right-hand sides that you want to solve for using the same matrix, right? So let's say I want to do something like ax1 is equal to b1, ax2 is equal to b2, and I've got, whatever k of those. I have k of those, right? Because the expensive part is doing the QR factorization, that's the n cubed part. You can do just the QR. You can just do the QR factorization once and keep it. And then for these parts, it's just going to be, you're going to have to do the multiplication by Q transpose and the back substitution, and both of those are n squared operations. And so that's kind of nice. Like if the only thing changing in your system is the right-hand side, which will happen, maybe more than you think, then you only have to solve once, and then you can do the rest of these things just doing the faster n squared operation. And actually, one example where that is going to come up is, so this was all showing us how to solve for a system of linear equations like this, right? But what we did not do actually was to find A inverse, right? We didn't explicitly create some matrix A inverse. We created a Q and an R, and we were close because we said R inverse Q transpose is equal to A inverse, but we never actually made A inverse. We could find R inverse and then do this multiply, but we can also solve for it. More directly, right? So let's say, so we want to find something where we say A inverse is equal to I, right? We can break this down into columns and do a series of solves. So I'm going to draw my handy little diagram here like this, where I have A times A inverse, right, is equal to I, right? And I can break that down as n column solves, right? So the column A1 is just going to be A times some, well, maybe I should call it something else. Let's call it B. We'll say this whole thing is going to be B here. So then I can say AB1 is equal to E1, right? And similarly, A times B2 is going to be equal to E2, right? We can break it down and solve a column of it at a time. And then using that exact same trick we just talked about, we solve for QR, right? And all we have are just different right-hand sides, E1, E2, E3, going down the way. And so we solve those and we get all of the B's, and we put them together. B1 dot 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 Bn is equal to B, which is equal to A inverse. So if we wanted to find the inverse of the matrix A, we could do that doing n of these back substitutions. And so if you think about it, the QR factorization, that's also about n cubed operations. And then we're going to do this back solve that's n squared, and we're going to do that n times, one for each column. So it's another sort of n cubed amount of work. So it's more work to explicitly create the inverse than it is to just solve for one system of linear equations. But you can also do, find the whole inverse using n-cubed operations. And so sort of like taking a step back here, this general idea of factoring and then solving has broader applications. We won't go into it a ton in this book, but in general, this thing where we said, we have some ax equals b, we turn this into qr, and then we solve the QR system. Well, so for one thing, there's other ways to do the QR factorization than the one that we've shown. There's something called Givens rotations. There's singular value decomposition. But there's also another way called the LU factorization. We're not going to learn it here, but I would not be surprised if you see it at some point. So the idea here is that we're gonna factor A into a lower triangular and an upper triangular matrix. So we end up with something where we have an L and an R, or an L and a U. They call it U instead of R in this one. And then we do two back substitutions. Solve the L part first and then the U part. So if we had some AX equals B, then we end up with LU, X equals B, and then this is just going to be something. So let's solve LY equals B using back substitution, right? And then we solve UX equals Y using back substitution again, and that will give us X, right? And that one tends to be just like slightly faster than the QR. There are reasons to use the QR factorization, and it's very nice for us, like from a theoretical point of view, to keep this one around. But you may see that LU factorization also, and it's the exact same trick, where we factor it first and then we solve. And similar to the other one, if we wanted to solve for multiple right-hand sides, we could, or reconstruct the inverse, we could. So yeah, okay. So this is the big thing. If we're trying to solve a system of linear equations, sort of big picture idea, we take the matrix A, we factor it into Q and R, multiply by Q transpose, do back substitution to solve the R system, and we get our solution. And in the case where everything is square and invertible, we're done, and it's beautiful. So in future videos, and this is already long, in future videos we'll go through some examples and talk about pseudo-inverse. But yeah, feel good about it. We got through this whole big thing, and we're here now. So great. You did it. Yay.